Okay, I'm already seeing this one chatting. We gave you the instructions, but you cannot follow. I hope you all get that message and do the needful. Okay, let's proceed. The diagram is here. Having known the raw materials which are used to prepare hydrogen sulfide gas, we now look at the diagram. The diagram is here. Those who have just joined, we are saying the raw materials are iron 2 sulfide and dilute sulfuric acid. So in dilute sulfuric acid is a liquid, or dilute hydrochloric acid, it is put in the fissile funnel, as you can see, and iron 2 sulfide is a solid, and we put it in the flat bottomed flask, and our hydrogen sulfide is formed and it is collected over water. But remember, we may require the gas when it is dry. As the acid reaches the iron 2 sulfide, effervescence begins, and that effervescence is for hydrogen sulfide. That effervescence is for hydrogen sulfide, and it is collected over warm water since it is soluble in cold water. If it is required dry, we can pass it over anhydrous calcium chloride, and then it is collected by downward delivery because it is denser than air. Now, this is the equation for preparation of hydrogen sulfide gas. We have iron 2 sulfide. We are adding hydrochloric acid and we form iron 2 sulfide gas plus iron 2 chloride. Now, someone may ask you, listen to this. State what is observed when hydrochloric acid dilute is added to iron 2 sulfide. Last time we looked at iron 2 sulfide as a black solid. This is a black solid. And iron 2 chloride is a green solution. This is a green solution. Even iron 2 sulfate is a green solution. So the color of iron in solution is green. So if I ask you what is observed, you will say a black solid dissolved. Yes, a black solid. This is the black solid for iron 2 sulfide. Then it dissolves in the acid, of course, and since there is a gas, there will be effervescence. So a black solid dissolves, forming effervescence of a colorless gas and a green solution. And a green what? Solution. The green solution is for iron 2 chloride. The green solution is for iron 2 chloride. So take note of that. Even iron 2 sulfate is green. We are saying NB. Last time I asked you this question and you failed it, yet I had given you the answers. When we say concentrated sulfuric acid is not used to dry hydrogen sulfide gas, when I say explain why concentrated sulfuric acid is not used to dry hydrogen gas, please write the equations also. Write the equations also. So, like the other question I asked you for ammonia, why concentrated sulfuric acid is not used to dry ammonia? The answers are there in your notes. You are supposed to say, because ammonia reacts. No, I think we have not yet reached there. That is for some other class. But let's look at this. When I ask you to explain why concentrated sulfuric acid is not used to dry hydrogen sulfide gas, You must tell us that because it reacts, this is a marking point. So if concentrated sulfuric acid reacts with hydrogen sulfide, you cannot use it as a drying agent, because if it reacts with a gas, that means the gas will not be there. It will not be collected. So I repeat, we do not use concentrated sulfuric acid to dry hydrogen sulfide gas, because hydrogen sulfide gas reacts with concentrated sulfuric acid, and hydrogen sulfide is oxidized to sulfur, and the equation is here. When I say explain, please write the equation also. Write the equation, and the equation is here. 3 moles of hydrogen sulfide plus sulfuric acid. The products are sulfur and water, and we balance our equation. Please listen to me. What do we learn from this? The raw materials which are used to prepare hydrogen sulfide gas are iron 2 sulfide and dilute hydrochloric acid, or dilute sulfuric acid. Where do we get hydrogen sulfide? Where do we get iron 2 sulfide, which is reacted with hydrochloric acid to form hydrogen sulfide gas? Iron 2 sulfide can be obtained by heating a mixture of iron and sulfur. And again, we are saying hydrogen sulfide gas should not be dried by concentrated sulfuric acid, because concentrated sulfuric acid reacts with hydrogen sulfide gas, forming sulfur and water. Forming sulfur and water. Yes. The hydrogen sulfide prepared in this case contains impurities, especially hydrogen chloride and hydrogen. Physical properties. This is very important. We usually ask it in objectives. Hydrogen sulfide gas, it has a very bad smell. In fact, here we are calling it repulsive. Repulsive, meaning that anyone wants to repel it. It has a repulsive characteristic smell of rotten eggs. So whenever you see rotten eggs, there is only one gas that has a smell of rotten eggs, and that gas is hydrogen sulfide. Take note of that. It has a smell of rotten eggs. It is very poisonous. We have talked about that, but not as dangerous as carbon monoxide. You remember I told you the other poisonous gas is carbon monoxide. I think I'm the one who taught you that carbon and its compounds, and I remember telling you about carbon monoxide that should not be prepared in poorly ventilated rooms. I think you remember that. Try to remember. It's slightly denser than air, and that is why it is collected by downward delivery. So these physical properties, easy for you. It dissolves in water, forming a fairly weak acidic solution, and the equations are here. So the solution of hydrogen sulfide, when it is dissolved in water, it is acidic. Chemical test for hydrogen sulfide gas. How can we know that this gas we are dealing with is hydrogen sulfide when we are in the lab? Number one, we have already talked about this, that it has a repulsive smell of rotten eggs. There is no other gas. Once you are in the lab and you smell a gas with that rotten egg smell, don't think twice. That gas is hydrogen sulfide. It is the only gas with a rotten egg smell. It has a rotten egg smell. Now, how else can we confirm its presence? We can also confirm its presence by bubbling it through a solution of lead to nitrate. By bubbling it through a solution of lead to nitrate. And what happens? A black precipitate is formed. A black precipitate is formed. And what is that black precipitate? The black precipitate is lead to sulfide. So when hydrogen sulfide gas is bubbled through a solution of lead to nitrate, we are saying we form a black precipitate. And the black precipitate is lead to sulfide. So we have two equations here. This is an ionic equation. This one is an ionic equation here. This one. And this is a molecular equation. So you can choose any one of your choice. Yes. So when hydrogen sulfide gas is bubbled through a solution of lead to nitrate, we get a black precipitate. So for us, when we say describe a chemical test for hydrogen sulfide gas, for you say bubble the gas into a solution containing lead to nitrate, and the observation is a black precipitate. Let's move on. So we are running something from the test of hydrogen sulfide gas. Number one, it has a smell of poison. I mean, it has a repulsive smell of rotten eggs. And for the other test, we can bubble it through a solution of lead to nitrate, and we form a black precipitate, and the black precipitate is lead to sulfide. So all compounds, actually all sulfides, compounds of sulfides, they are black, except zinc sulfide. For zinc sulfide, it is a white solid. But the other ones, iron 2 sulfide is black, copper 2 sulfide is black, lead 2 sulfide, we are saying it is a black precipitate. So take note of that. Take note of that. Now that is enough. Don't bother so much about these equations. We rarely ask them. We rarely ask them, but you can just look at them. Like I told you, I'll be explaining what is just important, very, very important. So I'm now taking you to oxides of sulfur, and we begin with the most common oxides of sulfur, and there are two. There are sulfur dioxide and sulfur trioxide. How are these oxides formed? They are formed by reacting oxygen and sulfur. Another person may ask you, what is the class of these oxides of sulfur? Remember, sulfur is a non-metal, so its oxides, they are acidic. Sulfur dioxide is an acidic oxide, and sulfur trioxide is also an acidic oxide. Let's begin with sulfur dioxide. Very, very important. Among everything that we have looked at, please don't forget sulfur dioxide gas. Sulfur dioxide gas, how is it prepared in the laboratory? We have two reactions and they are all common. We can ask and be specific and tell you which one to use. When we use copper tannings or copper metal and we want to prepare sulfur dioxide gas, now this one has a condition attached. When we use copper metal and we want to prepare sulfur dioxide gas, we must use it with concentrated sulfuric acid. We must use it with concentrated sulfuric acid. I repeat, the condition for using copper metal to prepare sulfur dioxide gas, you must use concentrated sulfuric acid. If you have your notes there, underline this like 4 times. The condition for preparing sulfur dioxide gas using copper metal or copper tannings is sulfuric acid must be concentrated. And you hit also. Now, another method, part B, is by using sodium sulfide. We can use sodium what? Sulfide. But when we use sodium sulfide, the condition is sulfuric acid must be dilute or hydrochloric acid. So when we use sodium sulfide, we can use sulfuric acid or sodium sulfide. Sodium sulfide, not sodium sulfate. And remember, sodium sulfate here, it will be SO4. We are using sodium sulfite and dilute acid like dilute hydrochloric acid. The diagram is here. I told you we also need to heat if we use copper metal. But if we wanted to use sodium sulfite instead of copper here, this will be sodium sulfite and this will be dilute. You can use dilute hydrochloric acid or dilute sulfuric acid. So this is my heating, and you know the diagram, the flask cannot support itself, so it needs a stand or a clamp. This is a retort stand. Concentrated sulfuric acid is a liquid, so it is the one that is put in the thistle funnel. Now, sulfur dioxide, I already told you that it is an acidic oxide. What does that mean? It means it can be dried by concentrated sulfuric acid. Because being an acidic gas, it cannot react with concentrated sulfuric acid. So the drying agent here is concentrated sulfuric acid. It is the one used to dry sulfur dioxide gas. It is used to dry carbon dioxide gas because those acidic gases do not react with concentrated sulfuric acid. Now, sulfur dioxide is again denser than air, so it is collected by downward delivery. Now, your diagram, at the end of it all, they must be on the same level, such that you can, because you will be putting them like on a table. Place copper metal in the flask and arrange the apparatus as shown above. Gently heat the mixture until it is hot. We only heat when we are using copper and concentrated sulfuric acid. Effervescence occurs, and as sulfur dioxide gas is being given out, and the equation is here, but this equation is not balanced. It is not balanced, therefore, shall need to put here a 2. Yes, such that oxygen become 8 is we shall put a 2 on sulfuric acid here and a 2 on water, and that's when the equation will balance. Take note of that. We shall put a 2 on sulfuric acid and a 2 on water. The gas is passed through a wash bottle containing concentrated sulfuric acid to dry the gas. That one is common knowledge to you, and it is collected by downward delivery. So, you people, the way of preparation of gases does not change. It does not change. You only need to know raw materials, the substances from which the gas is prepared, the drying agent, the equation, and the method of collection. Then you can prepare any gas on Earth. Laboratory preparation of sulfur dioxide from sodium sulfite and hydrochloric acid. That one I already talked about it. But here, this is another mistake also. we shall collect that in the notes. Now this one is not supposed to be copper metal. It should be sodium sulfide. This is supposed. The procedure remains as shown. However, if the reaction slows, the flask may be heated gently. So this one is supposed to be sodium sulfide. In fact, if you check in Arthur Atkinson, for them they are using concentrated acid, but I repeat, both concentrated acid and dilute acid can work when you are using sodium sulfide, but only and only concentrated sulfuric acid will work when you are using copper tannings. So this one is supposed to be sodium sulfide. Please take note. We shall correct it in our notes. It's a mistake. And the equations are here. Here are the equations. Sodium sulfide plus hydrochloric acid will form sulfur dioxide gas plus sodium chloride plus water. Sodium hydrogen sulfide can also be used, and when it is used, the equation remains the same as you can see here. Physical properties of sulfur dioxide gas. It is also a poisonous gas. It is colorless with a characteristic pungent smell, pungent or choking smell. Yes, pungent. And if you look for the meaning of the word pungent, it means a very bad smell. It is acidic gas. So sulfur dioxide gas is an acidic oxide. We talked about it. It is very soluble in water, forming sulfurous acid. Now, sulfur dioxide being an acidic gas, it means it can react with sodium hydroxide, because sodium hydroxide is a base. I think you studied acids and bases in senior 2. So sodium hydroxide is a base or an alkaline solution. So if it is a base, then it reacts with acids. So it can react with an acidic gas, sulfur dioxide. And the same reason why it reacts with carbon dioxide. So sulfur dioxide reacts with sodium hydroxide, and the product is sodium sulfide plus water. When sulfur dioxide is in excess, hydrogen sulfides formed. So if you have excess sodium, if you have excess sulfur dioxide gas, then instead you will form sodium hydroxide. You will form sodium hydrogen sulfide. I will end with the most important thing about sulfur dioxide. How do we test for sulfur dioxide in the laboratory? In the laboratory, actually, every gas has its chemical test. And I'm saying the chemical test for sulfur dioxide in the laboratory is acidified potassium dichromate. Acidified potassium dichromate solution. Now, don't mind the equation, but at least know that acidified potassium dichromate 6 solution is orange. Acidified potassium dichromate solution is orange. So the chemical test for sulfur dioxide gas is bubble the gas in an acidified solution of potassium dichromate 6. And what happens? The solution will change from orange to green. So the chemical test for sulfur dioxide gas is by bubbling it through an acidified solution of potassium dichromate 6. And in that case, the solution changes from orange to green. Potassium permanganate also behaves in the same way, but for it, it changes from purple to colorless. But this is what we use. Unless we go ahead and ask you about potassium permanganate. but this is what we use. And that shows the sulfur dioxide is a reducing agent. So the chemical test for sulfur dioxide, you people, I repeat, it changes potassium dichromate 6 solution from orange to green. Note that somewhere, sulfur dioxide gas, when it is bubbled through a solution of acidified potassium dichromate, the acidified solution of potassium dichromate 6 changes from orange to green. And I want 2 questions now, and we stop. But take note of that. If acidified potassium dichromate changes from orange to green, and that is the effect of sulfur dioxide. I want any 2 questions from you. Any questions?